So hi everyone. Today we are going to discuss AVL trees. AVL trees invented by GM Edelson, Valeski and EM Landis in 1962. The tree is named after AVL in honor of its inventors, right? So AVL tree is a self-balanced tree that follows binary search tree properties, right? And created by these gentlemen. So AVL tree can be defined as height balanced binary search tree in which each node is associated with a balanced factor which is calculated by subtracting the height of its right subtree from the left subtree. So if for each node we will calculate the balance factor. So balance factor will be calculated through left of height and right of height will subtract. If the left or right, when we subtract this from the left, the answer should be come between from minus 1, 0 or 1. Other than this will be balanced, right? So balancing happen in a logic, right? So balance factor of any node is 1. It means the left subtree is one level higher than the right subtree. If balance factor is 0, it means left subtree or right subtree is equal height. If it is minus 1, then it means right subtree is having the more height than the left subtree. So as AVL tree, in this AVL tree we will calculate the balancing factor of each node, right? So let's start with the bottom. 65, no, child, it means it is 0. So 25, 65, 85, 125 and 175, they all have the 0 balancing factor. Now if we look into it, for the 75, so 75 left is 1, right is 1, 1 minus 1 is 0, right? And let's look at 50 now. 50 has one height in left subtree and two height in right subtree. So 1 minus 2 is minus 1. uh, if we'll go same for 150, left is 1, right is 1, 1 minus 1 is 0, right? And if we look for the 100, 1, 2, 3, 3 height for the left, 2 height for the right, 3 minus 2 is equal to 1. So that's how we look at the subtree. Each node has the balancing factor from minus 1 to 1. Minus 1, 0 and 1. No one should reach to other than these numbers, means 2 or minus 2. If they reach to this level, means we need to rotate this tree to balance out their left or right subtree. So, what kind of operation we perform? We'll perform insertion, we will perform deletion, and the AVL's tree will always perform this as a binary search tree, and they'll follow the basic rule of binary search tree. So, what is a binary search tree? So, binary search tree is like, if we are entering a number, right? So, 10, 15, 5. So, this is binary search tree. If you look at over there, why it is a binary search tree means left subtree should be smaller than the root and the right subtree is bigger than the root, right? This is the basic logic of binary search tree, and there should be only two child to each node. Now rotations, right? So whenever we will look at the AVL tree, whenever they are going outside the balance, means if they reach anywhere other than minus 1 to 1, then it means we need to balance them out, right? So that they will be again the AVL tree. If they are not balancing themselves, it means it's not an AVL tree, right? So there are four type of rotation: LL rotation, RR rotation, LR rotation and RL rotation. So LL rotation is, if you look at their name, LL means left subtree, RR means right subtree, right subtree, LR means left subtree, right subtree and left subtree. Let's start with the RR. So RR and LL is the easy rotations where we look at them. When BST become unbalanced due to a node inserted into right subtree of the right subtree, then we have to perform RR rotation, means anti-clockwise rotation we have to do, right? So like we tried to insert A initially, it is okay, then we inserted B, it is okay. The moment we inserted C, A's balance is gone off the road, right? So it becomes 2, and the highest is allowed in a AVL tree is -1, 0 or 1. 2 is not allowed, means we need to rotate it. So now it is inserted into right subtree of the right subtree, means we have to rotate them on an anti-clockwise, means we will pull it from here and rotate it like this. It means B will become the new root, and A become the left subtree, and C become the right subtree. And now if we look at over there, they all are having the zero, what to say, balancing factor. And left subtree is smaller than root, right subtree is bigger than root, means they are following the rule of binary search tree. And because their balancing is below 2, means they are following the rule for the AVL tree also. Now LL rotation. So if we inserted a node, because of that, balancing is gone off the road, that is on the left subtree of the left subtree, means A is inserted over there and C's balancing factor becomes 2. Now because it is this, we have to do clockwise rotation, and that is our LL rotation, right? And it is kind of right rotation. Now we'll try to same do the same thing. This will come, means B will be the root, A will be the left subtree, and C will be the right subtree, and all balancing factor is 0. Now these two are the easy one, right? Why they are the easy one? Because we are doing the one time rotation over there. Now if we look at the LR rotation, so LR rotation is means a node is inserted onto the left subtree of the right. So first we will go to the left subtree, then we inserted on the right subtree of the that left subtree. So means we can't do it a single rotation. If we try to do the single rotation of right or maybe clockwise rotation, then what will happen? A will become the root node, C become the right node, and B become the left node. And this is wrong. Why? Because it is not following the property of a binary search tree. Why? Because A is the root, B is bigger than A. It can't be on the left side. So B should be gone the right side, right? So for that purpose, we will do the LR rotation. LR rotation means first we will do the what to say anti-clockwise rotation to the subtree. So now if we will do the same, so what will happen? C become this, will come on the left part, and A become the subtree of the B, left subtree of the B. Now it will look like LL rotation. Now we will do the clockwise rotation to this. So after becoming this, means A, B, C, we will do the clockwise rotation, then B become the parent, and A become the left side, and C become the right subtree. If we'll do the same thing on the RL rotation will look like this, means first we'll go to the right subtree, and right subtrees, then we'll go to the left subtree. Now again we can't do the same easy rotation like anti-clockwise rotation. If we'll try to do it, what will happen? Again C will come in the root, A will come on the left, and B will come on the right. This is not following the binary search tree. B should be on the left of the C. So first what we will do, we will do the right rotation for the C. Then what will happen? A will come over here, B will come over here, and C will come over here. So when they'll become this, then we will do the anti-clockwise rotation. So after doing the clockwise rotation, what we will do? We will do the anti-clockwise. This become, then B become the root. After we will try to do the anti-clockwise rotation. A become the left subtree, and C become the right subtree. Now the balancing factor is 0 for everyone, and they are following the binary search tree rule also. Means left subtree should be smaller than the root, and right subtree should be bigger than the root. So now try to do this. Make a program in Java or maybe any languages. Try to enter these number. So if you will try to do this, I'll take you a little bit faster. So if we'll first try to insert this, H I J. The moment it becomes minus, they'll try to do the RR rotation, means anti-clockwise rotation, and this become the I H and J. means I become the new root, right? So that's how it will balance itself. Same thing will try to enter B and A. The moment B and A got entered over there, means they need to do the right rotation. So they'll do this, and B become the root over of the left subtree, and A become the left subtree of the B, and H become the right subtree. If we'll try to do this, the clockwise rotation over there, and IJ is there at the same place. Now, if we look at over there, 1 0 0 0 0 means it's a balanced tree. So now you all can go ahead and do the programming. We'll try to do the programming tomorrow. Uh, if you have any query or any other issue, you can comment it down.